Hello. So in this video we're going to talk about the Fourier series of a function. So for that we need a function f of x which is periodic of period t, and it needs to be continuous within the interval that we want to approximate it. So the Fourier tells us that the function is equal to a constant term plus a sum of sinus and cosinus, which are given coefficients, the Fourier coefficients. So we want to code a program that is gonna ask for a function, an interval, and its period, and is gonna find this sum of terms that is the best approximation we can do for that function with cosinus and sinus. Of course, we're not going to do sum till infinity because we're not capable of doing that, but you're going to see that even with a sum from 1 to, let's say, 30, we get a very good approximation of our function. So, to find the coefficients, we have to integrate the function times cosinus of 2 pi n over t. N is a variable that we're going to sum afterwards, and to find the other term, the bn, we have to do the same, but with the sinus. And the constant term is just the integral of f, and this constant term is equal to the mean value of our function within the interval 0 to t. So a few remarks: that the function f times sinus of 2 pi n x over t is periodic of t. Also, if you multiply f times cosinus, it's going to be periodic with a period of t. This means that the integral from a to a plus t of this function is equal to the integral from 0 to t of this function, which is going to be helpful if we want to approximate our function which has a period of, let's say, 3 from -1 to 2. So we're going to just do the same calculation that here, but we have to use this property. So we're going to just look at the code. Okay, so we're going to use the symbolic toolbox. So first we're going to define our variable x as a symbolic variable, and our function f, and s, which is going to be the series. So we want the user to type in the period, the input, and the degree of approximation. The degree of approximation is an integer that we're going to do the sum until this maximum value. Because we cannot do it until infinity, we're going to just choose a value to stop there. And then we're going to ask the user to give us a function. Of course, it has to be a function of x. So here you should put if to verify if the input is really an integer, because we need that, or if max is an integer. But I'm not doing it right now because it's not what I want to explain. So first we're gonna calculate the integral. You use the function int. You give it f, the function that you want to integrate. Just to be clear here, f is a function of only one variable, so we can integrate it only with respect to x. It's not needed to put this x, but it's better to put it for safety, because after, when we're going to multiply f times cosinus, you know that cosinus is also a function of n, because we have defined n symbolically. So we have to specify that we want to integrate with respect to x. So why here these two terms symbolize the beginning and the end of the integration. As I explained before, I did it because if we want to approximate our function from -1 to 2 with a period of 3, we're just going to use this. Like if our function begins at -1, we have to integrate from -1 to 2. So that's why the boundaries of integration look like this. If you just want to approximate from 0 to 3, you just choose b equals 0. So this is going to calculate our mean value, and then we are going to calculate the Fourier coefficients. Since we're doing it symbolically, it's going to give us a symbolic function, which is going to be just in terms of function of n. So we calculate, we say, do the integral of f times the cosinus of 2 pi times n times t over t. Hence that t has to be an integer or like a period, is not a variable. And then bn, we do the same thing. We integrate f times sinus, and then we're going to define a symbolic function as and bs, which are going to be all these terms. So this is one symbolic function that we have defined, and this is one symbolic function that we have defined. So this is going to be, all of this is a function of n and x, and we want to do the sum from n equals 1 to a maximum value. So we're going to substitute each time that the sum goes from, we do the sum for 1, no, then for 2, then for 3, we're just substituting n in our function as and bs. And that's what we're going to do with a for loop. So here we are using the for loop, and we're going from 1 to our maximum value, and we're just going to substitute our n by 1, then by 2, then by 3 in our function as, which is an that is a function of n, and our cosinus that is a function of n and x. And we're going to substitute in as and bs, and then this we're going to do it each time. Here we have to initialize something before we go into the loop, because we're going to use s. We have to give s an initial value, so we're going to do that, and we're going to say s equals a0. So s equals a0, and the first we're going to have a0 plus as evaluated at n equals 1, and so on until we reach our maximum value. And then we're just simply going to plot our function. Here I'm going to plot my Fourier series from our beginning to 4 times the period plus our beginning, because I want to show you the graph. And then we're going to plot also the original function to see how it's different or not. But we're just going to plot it once for b to until a period t. So we can now, it asks us our period t, let's say 2 pi. I want the beginning of my function to be, let's say, minus pi. The degree of approximation, I want to say 10. I'm going to do the sum from 1 to 10, the sum of n from 1 to 10. 10 is nothing compared to the infinity, but it's still going to be a fairly good approximation. And then we're going to enter a function, let's say x squared. And now I want to say something because of these warnings. So I'm using Octave, which is a substitute by MATLAB, but this, I've tested this code in both. So it gives me a warning and I've been to the code that gives a warning, and it's because this is going to give you results that are very imprecise for an, especially for 1 over pi. So an is going to contain 1 over pi, but 1 over pi, if you type it in, it gives you a finite number. So what the computer is going to do is that it's going to replace 1 over pi by 113 over 355, and you see that 113 over 355, if we say that minus 1 over pi, is going to give us minus 2 times 10 to the power of minus 8, which is practically 0. This is important because now we have gotten our series, Fourier series, and we can see that it's basically the same. And that it continues and is going to give us a periodic function. So we know that it is a sum of sinus and cosinus. So let's say we want to see how the coefficients look like. So let's just type an. An is, as I said, a symbolic expression, and it's only a function of n. You see that the x's are now gone. So I said that 113 over 335 is 1 over pi. So here we will have 1 over pi. If we wanted to write this down on paper, would be better to do it that way. But another thing that we see is that because this program doesn't know that we're going to substitute n with only integers, it's not going to simplify these expressions, because sinus of pi times an integer is always 0. But maybe the program thinks that we might just replace n with 0.3, in which case this term, and this term are not 0. So you have to look more carefully into the coefficients. And let's take a look at Bn. So Bn is 0. Why is it 0? If we take a look at our function, we know that x squared is not an even function. So for even terms, for even function, the coefficient Bn, which is going to be multiplied by a sinus, is always 0, because the contribution to approximate an even function with sinus, which is a not function, sinus does not contribute anything. So this code is not perfect. I'll be happy to get some feedback, but what I want to tell is that, for example, this code uses integration. So it finds the integral of the function, but there are some functions that you cannot integrate in terms of previously known functions. For example, if you want to do, let's launch it again. If we want to do the integration of a function, let's say x divided by x plus 1, and this function is going to be multiplied, by a cosinus, and then it's going to be integrated. So this function multiplied by a cosinus, you cannot analytically integrate it. This is going to just stop right here. The code is not going to do anything else, because it cannot integrate it analytically. So this is gonna be the topic for my next video, because I have a couple of codes that can do the Fourier series for functions for which the product of the function times a sinus cannot be integrated analytically. And I also have another code that is useful for functions defined piecewise. So we'll see that in our next videos. Thank you for watching.